Hi, I'm Stijn Omus, and today's lesson will be about a novel concept. It's called visual spread, and it's a variant on visual angle. So, for example, this camera has a field of view of about 70 degrees. I had to look at my note there. 70 degrees, and the width of my head is about 10 degrees. 10 degrees visual angle. But we're going to modernize this concept. And what is needed for that is a new geometry, a new mathematics, rational trigonometry it's called. And instead of distances, rational trigonometry talks about quadrances. And instead of angles, it's talking about spread. So that's the spread that comes back in the title, visual spread. So eventually we're going to talk about the visual spread of an object. And it turns out that the visual semi-spread, say half the spread, that's not correct, but just to give you an idea, but that turns out to be the easiest way to think about it and a really elegant solution. But let's get into some mathematics first. Oh no, we're going to do the visual angles. Just to give you a sense that if you keep your thumb at arm's length like this, then the width is about 2 degrees. If you do your hand at arm's length, it's about 10 degrees visual angle. So just to give you a rough idea. Now let's go into the mathematics. So rational trigonometry was created by Norman Wildberger, and you can read it in his book Define Proportions. That was published in 2005, and I can highly recommend his YouTube channel. You can find everything about what I'm gonna summarize today here. And rational trigonometry is about the geometry of triangles, as the word says. And in the formulation of Norman Wildberger, it's only about rational numbers. So numbers that you can write as A over B. And as I mentioned earlier, so distance D now becomes quadrans Q. And you can think of that as Q is the square of D. And the angle alpha, we will now turn it into a spread S. And the spread S is basically the sine of the angle alpha squared. It's not, this is very important, it's not defined that way. It doesn't need sine, cosine, tan, all those, I'm blanking on the word here, but those type of functions we don't need. So let's get into it. Let's start with a right triangle. And it has length ABC, small a, small b, small c, but in the parlance of rational trigonometry, those are quadrances. So it's big A, big B, and big C. And maybe you can already think ahead, because the Pythagorean theorem is valid here, and it's simpler. So it's A plus B is C. So there's no squares there. So at some point we're going to take advantage of this, that it's now linear instead of quadratic. And of course that only works because we have a right angle on the bottom right part of the triangle, the blue point there. So now we're going to define spread S, and I've denoted it in the left bottom corner. So it's the spread between the segment B and segment C, and it's simply defined as the quadrants on the opposite side, that's A in this case, over the hypotenuse quadrants, and that's C in this case. So it's A over C. So a spread is a simple proportion of quadrances. So note again, there's no sine, no cosine, no tangent, no tan functions. Simple proportions. And this will simplify a lot. So what do we have now? Well, we have those two simple formulas. And in this case, I'm using, this is the only thing I need for the rest of the story. Rational trigonometry is much richer. It has 3 basic laws that are really interesting, and you need to learn them. But this is enough for now. So let's move to optics, and I want to mention Euclid, who is famous for the Elements, the geometry book in the last 2 millennia. And he also wrote a book on optics, and it's the oldest known book that has some sort of mathematical theory on vision. So that's why I'm interested in it. And let's look, because he also formulated it in terms of postulates. Let's look at his first postulates. He says rectilinear rays, so basically light rays go straight, and they're diverging from the eye. And Euclid thought that light comes out of the eye and goes into objects. We don't think that anymore. But mathematically, it's enough for us. Let's go to the second postulate. He says, the figure contained by a set of visual rays, all the blue lines here, is a cone of which the vertex is at the eye on the left and the base at the surface of the object seen. That's the sphere, the red sphere on the right. Let's look at that in detail. So the cone is the blue lines. So we don't need all those lines, we just need 2. Well, let's look at that in 3D. We need the yellowish green cone. It's a spherical cone. I'm sorry, a circular cone. And that's what we need. So let's move on and, oh, I'm skipping one. So the vertex of that cone is on the left, it's the eye. And the base of the cone is all the light rays that graze the surface of the object. So we have a viewpoint, we have a visual cone, and an object, in this case a sphere, to keep it simple. And now we can do geometry and apply those lessons that we learned from rational trigonometry. And the first question is, shall we do the visual spread like the visual angle? That it's the angle, the opening angle of the entire visual cone. Well, it turns out it's easier and you get nicer mathematics in terms of algebra to do the semi-spread. And this is what I mean by the semi-spread. So if you take the viewpoint, the blue viewpoint on the left, and the green point, the center of the sphere on the right, then P is the spread between that line and one of the light rays that graze the surface of the sphere, and that we call P. So now let's get into the derivation and find the formula for this. So we can see that we have a right angle, so the radius and the light ray make a right angle, so that's interesting. So we have a distance D, well, distance in quadrants, of course. We have a radius A in quadrants again, and the semi-spread P on the left there. So now simply we take the opposite quadrants over the hypotenuse, and we get a really simple equation that P is A over D. So that's nice, and it's much nicer than the alternative. So this is applicable to a sphere, but also to a circle in 2D, and in future lessons I will use either one. So it's nice to make a graph of this. So if we look at the case for A is 2, so the radius is 2, so that means that for if D is also 2, then P is 1. So basically if you have a sphere like this, then you're like so close that the basically your eye is at the surface of the sphere. So it takes up your whole visual space. Visual field of view. And then for these that are higher than A, it nicely shows the graph, the 1 over D graph curve. So if we compare this to the classic visual angle, then there is an arc sine and the E over 2D. Well, of course this is similar and also correct, but it's not so easy to see unless you're very familiar with the arc sine function to see what the relations are. And since the P is A over D is a simple formula, it's way easier to grasp and to work with. So let's now apply this to the sun, the moon, seen from the Earth, and the reason why a solar eclipse actually happens. Basically, that's when the moon gets in front of the sun and exactly covers it. So let's look at distances and radii. So the radius of the sun is way larger than the radius of the moon. The distance of the sun is way larger than the distance of the moon. And the visual semi-spread is the same up to the 5th digit there, and only in the 6th digit they start to converge. So the visual semi-spread of the moon is slightly smaller. In degrees, it's about half a degree. I think you are familiar with that number. So the moon and the sun is about half a degree visual angle. And you can check that. So if you put your thumb up to the sun or the moon, it should entirely cover it. So what do we have? We have a redefinition of the concept of a visual angle of an object, and I call it the visual semi-spread, and in this case of a sphere, and it's a simple formula. P is A over D. And it's also an insightful formula. So for example, if you have an image of the moon, for example, you can only know P. From that image you cannot know if it's a big moon very close or a very, very big sun far away, because P is the same. So this already teaches you that just from one image, you can only know the proportion of size and distance, but not either one of those. So that gives you some direct insight. And it's, as we've seen, much easier than the classic formulations in terms of arcsine or arctan. So this concludes my lesson for today. If you want to know more, you can go to my website there. And thanks for watching. Bye.